Okay, so this is where we left off last time. Good morning, everyone. Good seeing everyone's smiley, happy faces. As a heads up, I will try to have some interaction in class with some of you. And so the lucky persons for the day are the persons whose last names begin with the letter B. So if your last name begins with the letter B, guess what? I may call on you. Don't be shy. Comply, right? So there's that component. We left off here last time where you want to find the probability of a sample of 4 women having an average height larger than 5'7". So of course you want to go ahead and go through those steps to kind of recap for you. What you want to do is say, okay, well, we want to find the z-score. That'll probably be like our first step. Well, first of all, you got to recognize that you have to do this new standard deviation, which is sigma over radical n, which will be, what, 3 divided by the square root of 4, which is 1.5, or 3/3. But that goes into the denominator. So recognize that you need to use this character somehow. Find the z-score. And then go ahead and find the correct probability. Now, those of you with the calculator, you can just use this function here, normal CDF, lower bound, upper bound, the mean, and here's the kicker right there. Okay, so as long as you have those 4 components, you should be in good shape. And I'm trying something new where you turn out the lights right next to it. So make it probably a little bit brighter for you guys down here. A little more glare there, yes?
Will Stats Portal take both if you use the calculator or the chart? Because I did it both ways and I had a couple decimal places off.
Right, it should take both, and we're trying to make sure that there's enough latitude for that. So yeah, if you go 4 places, it should be okay. All right. Stats Portal is picky, unfortunately. Technically, the calculator is more precise than the table, believe it or not. Now, so that's an example from Thursday's class. So let's all walk through a fresh one today on Tuesday, a whole week later almost. So yeah, sure, there's a chance for one person to be taller than 5'7", but then on the flip side, 100 women having an average bigger than 5'7". Let's look into it. About 9. This height should be height. All right, so you have 9 women. The chance that their average is more than 5'7". So the probability that the sample average is bigger than 5'7". Same old steps. 67 minus 64. But then because you have this sample size of 9 involved, you got to consider that somehow. Okay, and again, just for those who are just joining us, x bar minus mu standard deviation over radical n is the formula you want to use here. And that's how I got that guy. What's that? 3 over 1. Okay, so 3 over 1 will become 3.00 minus that. So that's the probability there. And again, in the calculator, it's going to be this. Lower bound is 67. Upper bound is some arbitrarily large number. But then you have to put the entire thing in, the entire expression, 3 divided by radical 9, which of course is just 1, but indulge me here and put the whole thing in. And I got my calculator also. Point 0013. So in this case, we get the same answer exactly, probably because the z-score is further out in the tails. So in red, I guess I use the table to get that solution. Here I use a calculator. So again, the key steps: find this. Make sure you use that formula there. Find the z-score right there, and then of course go ahead and subtract from 1 if you need to. Okay, and so let's kind of recap here. Why does the probability of interest decrease as the sample size increases? Well, let's just kind of take a peek. So when we have n equals 9, the probability that the sample mean was bigger than 5.7 was 0.0013. When n equals 4, I think, yes, this one here, the chance was 0.0228. And then in the very first case, for one woman, it was 1587. So if you look through your notes, we did 3 examples, and you guys can probably see it more clearly than I can on the slides. The probability got smaller and smaller and smaller. Well, why does that happen? What do you think happened? People whose last name starts with B.
Mathematically or logically?
Both. Mathematically first.
The denominator is getting smaller or larger?
Smaller, right? Okay, so right. So let's kind of have 2 components to this. Let's say mathematically, in each case, the first time we divided by, I say, the standard deviation, if you will, was just 3. And then the standard deviation, quote unquote, was 3 halves, or 3 over the square root of 4. And then it was 3 over square root of 9. So in each case, like he's saying there, we're dividing by a smaller number, which means our numerator stays the same, divided by a smaller number. Our z-score is getting further and further away from 0. So yeah, mathematically, we're dividing by smaller standard deviations. So standard deviation is decreasing, means our z-score is increasing, which means that we are further from 0. So the further we are from 0, the less likely the event is, because it's out in the tails. Now, from a practical standpoint, so that's the mathematical side, if you will. Now, practically, sure, you walk down the street, you see what's the chance of one woman having a height above 5'7"? It's likely, all right? But the more people you sample, the more things should behave the way they're supposed to, Okay, so the average should kind of get closer and closer and closer to the true mean there. So practically speaking, the larger your sample size, the more precise your data should become. I would say should be for lack of room, I guess you could say. Okay, or become is what you should write down. So we should get closer and closer and closer and closer to the true population mean mu of 5.4. And then mathematically, you kind of see the standard deviation getting smaller and smaller and smaller and smaller. Therefore, both sides work out. Mathematically and practically, things kind of make sense. All right, in the on-deck circle, get ready, Celeste, John, Bailey, Brooke, Sierra, Haley, and Brian. So be ready if I might call on one of you guys. Okay, so let's see here. Well, what if we don't know about the true population mean? Well, we're in luck, all right? So we have a so-called rule that we can use. And so in general, distributions become more and more like a normal distribution. That's no problem. And so we have the so-called central limit theorem. All right. So in general, things behave a little more like a normal distribution with some mean and some standard error of a square root of n. And that's our new character, the so-called central limit theorem. And we call it the CLT, not to be confused with the TLC. Let's see here. Yeah, so central limit theorem. There we go. So what does that say? So it allows us to be flexible, and we can kind of relax that normality assumption. So as long as we have a distribution that's large enough, we can assume normality. So, so the CLT allows us to work with non-normal distributions. As long as the sample size is large enough. Okay. And you may say, well, how big is large enough? Well, non-normal distributions. So it doesn't have to tell us explicitly that it's from a normal distribution. We can just kind of see what the sample size is. How large is large enough? Well, in our cases, anything that's at least 40 is large enough for our purposes. Okay. It looks like they tried to solve the heating issue, so we do not have our contraption plugged in, but it does feel pretty good in here so far. All right, so then what about these conditions here? Well, again, more filling in the blank, not a whole lot filling in the blank. This screen is always a little bit clearer than that one. So we have a few conditions to check out. The first one is that you must still have a random sample. Okay, we talked about that in chapter 8, I think it was, chapter 8. So if you have a random sample, then you didn't purposely invoke any bias into your research, so it should be A-OK. So you need a random sample. Then there's a so-called small enough sample, or small enough condition. So we assume independence here, I guess you could say. But if the population is at least 20 times bigger than the sample, everything should work out just fine. So this guy, these two are interchangeable. Either we have a small enough sample or we have a big enough population. Either way, we're saying that the sample size or the population is at least 20 times the sample size. Either way, it's saying the same thing. And then, of course, yeah, there's our condition there about a sample size being at least 40 values. So a small enough sample or large enough population, and then large enough sample. Take your pick. And then the TI graphing calculator, we talked about this a little bit already. You can use JUMP to figure these out, or you can use a calculator. So here are the steps. Second bars, normal CDF, and then here's our favorite components. Lower bound, upper bound, mean, and then that guy. Standard deviation or radical n. And so this is just a little disclaimer here for you to be aware of. Then we'll be talking about sample means. Okay. And of course, on an exam or a final, we will not be as picky as Stats Portal, obviously, with the rounding issue. Okay, so everybody loves koalas, right? They're cute, they're cuddly, they make you laugh. All right, let's look at how they behave here, if you will. All right, they're nonviolent. Okay, so let's go ahead and work on a couple examples real quick using our knowledge of the central limit theorem. So notice how I don't say that they're from a normal distribution, right? As long as the sample size is large enough, we can assume that the data will behave approximately normal, I guess you could say. So here we go. Key things to jot down. Koalas weigh between 15 and 30 pounds. That's kind of background information. The average weight for a koala, so we're thinking that maybe all koalas around the world is about 20.7 pounds, 7.5 pounds. The standard deviation for some koalas is 3.05 pounds. And maybe we have a sample size of 45. You have those three components, you're good to go. Good to get started. All right. The first, now you have 3 questions, I think, on your notes. Yes, 3 questions. So, and then I had 3 people. Let's see how we got here. So let's talk about my dear friend is John Bailey here. Now you may say, I'm not going to raise my hand. He won't know who I am. All right, that's okay. Well, Brooke Baker. All right. About Celeste Bacon. You're right there, Celeste. Thank you for being brave. Not that those other 2 weren't, but you definitely are brave. So Celeste, you're ready for that one. Okay? Now you have parts B and C. Is Sierra Bartholomew here?
I am, but I haven't been here, so I don't know what's going on.
Okay, that's okay, Sierra. We're here to help. All right, so Sierra and company. All right. Sierra, Celeste. Where's Haley? No Haley Beck today? This is bad luck. All right. Brian Bishop. Ooh, you guys. All right. See, I'm not playing. Kara Brown. We only have half the people here. Lucas Boring. Lucas, my man, you came to my office. I remember you, Lucas. Hilliard, right? All right, represent. All right, so let's see here. Lucas. All right, so here's what we're going to do. We have 3 brave draftees, not volunteers, but draftees. Okay, if you are in Celeste's side of the room, right over here, I want you to work on this one right here. I think it's part A for you guys, right? Okay. If you are with Sierra and you're in the middle, okay, work on part B and help Sierra out, right? Because she hasn't been here. Now, last one. If you're with Lucas, let's work over here. For those of you on the far left, work on part C with Lucas. Got it? Got it. So I'm going to turn you loose for a few minutes to start working on these, and then we'll discuss them as a class. Now, we did a few examples earlier about heights of women, so you can look at that for a reference point. All right, so I've set all of you up. Now let me kind of come around there and see how my good friend Sierra is doing. Yeah, wet. Oh, bummer. All right, so you're doing good. All right. You guys had a big midterm last Monday, and you kind of relax and recover. Now we're kind of getting back on track. All right, Celeste. Ready? Sure, she says. Okay, Celeste. So you got these koalas. 21.3 is a... And what'd you do? Celeste, well done. Okay, what Celeste did was just use that formula, x bar minus the mean over sigma radical n. And then you have to be careful, Celeste, because there's some kind of mathematical mysteries here. Did you get a z-score here? What'd you get? 1.21. Does the Celeste contingent agree with that process? They don't disagree. All right, so 1.21. And Celeste, you want the area bigger than 1.21. If I go into my chart, 1.21 is 0.8869. That's what I get. Okay, and then Celeste, what do I do with this 0.8869? Perfect, perfect, perfect. Gold star or red star for Celeste today. All right, so then she'll do 1 minus 0.8869, 1131. Now some of you say that's the old school 20th century way of doing it. I had this cool calculator. I'm gonna do it that way. That's fine. So then you would do normal CDF. The lowest number is 21.3. There is no high number. You could put like 1 million if you wanted to. Okay, we'll say like 1 billion or whatever.
Wouldn't it be 30?
Oh.
That claws are between 15 and 30 pounds.
Yeah, I guess that's pretty safe. No need to go to a billion, right? A billion-pound koala? Probably not realistic. Okay?
What's the point of putting that there between 15 and 30 if those aren't the boundaries?
It was a distractor.
Oh, man.
Okay. So then there's that. And then 3.05. No, 20.75, excuse me. And then I like to put this all in one parentheses. So 3.05 divides square root of 45. Now you could do it in one separate step. 3.05 over radical 45 equals, and then plug that number in, but you can just keep it all together. .1132. Okay, the question was raised earlier, will Stats Portal take, which answer will they take? As long as it has plus or minus .0001, these answers are within 1/10,000th of each other, so we're good either way. Okay, so .1132 is correct, 1131 is fine also. Red star, Celeste. Next, Sierra and Company. You guys, I want to say this is an easy one, but it kind of is an easy one. So yeah, the probability that X bar is between 21.3 and 19.5. Well, you do the z-score for each one. And you get the two z-scores. Let's go ahead. Negative 2.75 for this one. .21 for that one. 1.21 is 0.8869 from the chart, and negative 2.75, 0.0030. Yes. And because you want the area in between those two, you subtract them. .8839 is what I get. Yes, that's what I get. So I said previously that Part B was an easier exercise. It actually requires more work. You have to find the z-score for the left-hand side and the z-score for the right-hand side. But Part B is actually easier if you use a calculator. So, Miss Sierra, hello. How did you use it? How do you use a calculator to solve this one? Yeah. Normal CDF Sierra, 19.5 is correct. Perfect. I love how she said population mean. Awesome. Good use of vocabulary there. Right. Now some of you, I saw you using this, but you forgot the 45. So make sure you put the whole thing in there. And then Sierra, what did you get for the answer? Okay, so again, that's within that 10,000th, right? So that's totally fine. Now, usually around this time of the semester, two camps tend to develop. There's the Table A camp that finds the z-scores and then subtracts them, then there's the normal CDF camp that just says, I'll just plug it into the calculator. You should be thinking in your head which camp you're kind of leaning towards. All right? Perfect. Lucas, you ready? What you got for me, Lucas? Okay, so Lucas is already on top of it. So X bar at most 19.5. And then we're going to do 19.5 minus 20.75 over 3.05 radical 45. Negative what? 2.75? Okay, and then Lucas, what's that? 0.00? Yeah. And then, of course, on the calculator, it would be normal CDF. Where is Chris? Are you Chris, right? Chris, right? So, Chris, what would you put down for the limits for the normal CDF function here? Okay, right. So you're saying we were given earlier that koalas can be 15 pounds at the least, right? At the most, or the smallest number is 15 pounds, and then up to 19.5. So sometimes you can do like -1 E99 or some arbitrarily low number, right? You never have a negative 10-pound koala, but I'll put negative 10 in there. Okay? So then the mean is 20.75. And then you have 3.05 radical 45. .003, I guess. I get 299, but 3, I guess you could say, is the answer there. All right, so again, you should be deciding which camp you're in. If you're in the Table A camp or the TIA3 camp. And look what happens here, how convenient. I'm almost done with this, yeah, no. So, part C, the answer was .0030. Part B, the answer was .8838. Part A, the answer was .1132. What happens if you add up all those? You get about 100%. Okay? And if you look at your notes, it should make sense. In part A, we're saying at least 21.3 pounds. Part B is between 19.5 and 21.3. And part C is less than 19.5 pounds. So that covers the whole gamut. That, my friends, concludes chapter 11. All right. The key thing there is using that 3.05 with that standard deviation of radical n in your calculations. And give me a second to transition into 14. No problem. That's a good question for transition purposes. The central limit theorem is like an expansion of what we did a few pages back. A few pages back, we said if we know it's normal distribution, we do it this way. The central limit theorem says as long as the sample size is bigger than 40, it doesn't matter if it's normal or not. Okay. So think about it this way, like the example about height, right? 5'7" is a woman's height and that sort of thing. We always assume that it was normally distributed, but then the koalas, there's no mention about the koalas being normally distributed. So the central limit theorem allows us to kind of make that jump. Sleep on it. And I'll make a note here when we get to the next part. All right, so we're back. And here we go. So again, just a little to follow up. Normal, and I give you the mean, standard deviation, and sample size, I can find probabilities. But if I give you the mean, the standard deviation, and sample size, and the sample size is bigger than 40, then I can still find the same kind of probabilities. So yeah, the central limit theorem allows us to do the same calculations as if it was a normal distribution, if the sample size is bigger than 40. Capítulo 14, see? See. All right, so thank you for my volunteers, my draftees, for your help today, Celeste, Sierra, and Lucas. Tune in tomorrow on Thursday when people whose last names are letter D are on the hot seat. All right, but don't be absent. So let's see here. So far in chapter 14, we're going to take the midterm 1 material, put that as our foundation. All right. Then you learn some stuff from chapters 10 and 12, kind of add to the base of the foundation. And then you got this chapter 11, information about central limit theorem and sample sizes and so forth. So we're kind of getting ready for inference. Now, again, the so-called statistical inference component, if you will, just kind of helps us decide, make conclusions about the population from the sample. So again, you have your sample, you have your population, and then you can use inference to kind of make conclusions about the population. But again, the sample mean does not always equal the population mean, right? So you want some room for error. You want some so-called wiggle room, if you will. And we're kind of familiar with this concept. So in this case, X bar, give or take some room for error. So again, if you have this in your notes, if you will, you'll be jotting this in there. X bar plus or minus some room for error. And then now this notion of room for error is called margin of error in our textbook. And so we're going to work with the sample mean, give or take some margin of error. So our goal is to try to estimate the population mean mu, but we may never know that. So we'll take the sample mean, give or take some buffer, if you will. So that's a key component. And this will be a key helper to you this chapter as well. Actually going forward, this guy right here. So what do you need for this margin of error? You need the standard deviation, ladies and gentlemen. You probably need some kind of constant C based upon some z-score, probably. So I even call this guy some z-score based upon some constant C. And you need some sample size. So again, you need those three components, standard deviation, sigma, some z-score, C, and sample size. And here they are, the big three. And this is all ready for you to read later on. we will probably cover through the first example today, and then that'll be pick up the rest on Thursday. All right, so what do? Well, we have three conditions again in this chapter. SRS is a simple random sample. Okay, so that's the goal, is to have a simple random sample, but it may not be perfectly random. They talk a little bit about an exact normal distribution here. There's always room for error there. And it's kind of interesting. We don't know mu, but somehow we know sigma. So I always found that to be curious. But so that's how we lead into chapter 14 and 15. So again, these conditions are also often called assumptions as well. The big three, if you will. All right. So there are some simple conditions. You can read about them as well. That's fine. And here we go. So who was a psych major? No psych majors in here? Okay, your name again? Michelle. Michelle, the psych major. So suppose I'm interested in IQ scores and how smart humans are, right? I don't have the time or the money to talk to every single person out there in the world. But what I chose to do, so technically, I do not know what the true average IQ score for every single person in the world is. I don't know what that is. So the population mean mu is undetermined. I don't know what that is. But what I could do is use my Stat 1450 knowledge and get a pretty good idea of what it is. So what I'm going to do is take a sample of 49 adults, and then their average IQ score was 100, and maybe that can help me out. Oh, and then I've heard somewhere down in the past that the standard deviation for this is 15. So I could come out and say in Michelle's next paper that the average IQ score for all persons is 100. But that's a little risky. So what I'm going to say is that maybe the average is 100, give or take some margin of error, just to kind of cover my backside a little bit, right? So now I can kind of get a claim and use statistical inference to figure this out. So our goal is to try and figure out what that might be. Plus and minus. So to estimate the unknown population mean IQ score mu, which we don't know, we start with the sample mean x bar. That's no problem. And again, because what we learned in chapter 11, we look at the sampling distribution of x bar. So that's going to be, remember this guy? It was like a sigma over square root of n. (15/49). What's that? 2? Or a square root of 49, excuse me. 2.1429, if you will. (2.1429). If you put this in Stats Portal, I'll go at 2.1429. For our purposes, for demonstration purposes, we'll say 2.14. So again, in chapter 11, you learn, don't just take the standard deviation of 15. You have to look at 15 relative to its sample size with the square root of n involved. So now X bar has a normal distribution, maybe like 100 and 2.14. Okay, let's use the so-called new standard deviation or revised standard deviation, if you will. And here we go. So you remember this from way back when. The sample mean, give or take 1, I'll call this new standard deviation. The sample mean plus or minus 2 so-called new standard deviations. The sample mean plus or minus 3 so-called new standard deviations. And again, by new standard deviation, I refer to this guy. The standard deviation over square root of n. So we have here 100 plus or minus 1 times 2.14. Again, I'm just kind of truncating it down to 2.14 for now. 100 plus or minus 2 times 2.14. I did the math for you. Trust me, my friends. 97.86 up to 102.14. 95.72 up to 104.28. 93.58 up to 106.42. Okay, so let's kind of pause for station identification purposes here. You go out 1 standard deviation. So again, we're not going out to 15. That's too big. 15 over radical 9 or radical 49, that works. And look just like before. 97.86 to 102.14. It gets a little bit wider and a little bit wider. But the IQ scores, the sample average should still bounce around between 93 and 106.42. So I try to represent that here, and then you're like, oh man, he went too fast. Well, don't worry about it. All right. So here's 100, and let's say you got 1, 2, 3 standard errors, 1, 2, 3 standard errors that way. So here's our sample mean X bar. But the first interval went from here to here. The next interval went from here to here. And finally, so the range of IQ scores could bounce all over the place. But if you took a random sample of 100 people, their sample average should only bounce between 93.5 and 106.5. So we're pretty confident that even though we don't know what the true average IQ score is for every single person, from our statistical knowledge, I'm going to guess that the true mean is somewhere between 93.58 and 106.42, just by using some statistical theory. without talking to every single person out there in the world. All right? So that's kind of all laying the foundation for what we're going to do next in chapter 14. And it gets better, trust me.